Okay, YouTube, in this video we're going to be using the law of cosines to determine some unknown parts in a given situation. So I think that probably the hardest part of this is representing the situation to begin with. And you'll notice that I've already given you a diagram, which is a nice thing, but let's still read through this and discuss what it is that we're looking for. So it says a ship travels 60 miles due east, then adjusts its course northward as shown. So what we see here is that we've left from part A, this is our point of departure, and we went 60 miles to the east. We've reached some what I'm calling point B. And then I say I've adjusted to some northward course. Now, I'm not going directly northward, but I mean kind of tilted northward. If you would imagine this side going out, we have some angle kind of elevation towards the north here. So we say after traveling 80 miles now in this northward direction, so we have this side length right here. We say we've arrived at some point. We're calling this point C, or I'm calling this point C. And so already we know a couple of side lengths in this situation of some triangular situation. It says the ship is 139 miles from its point of departure. So from point A to point C, we see that this is a distance of 139 miles, and we can fill that in here. What I want to do is describe the bearing from point B to point C. So when we talk about a bearing, let's go ahead and change colors here. When we talk about a bearing, recall that we're saying that it's some direction that we're heading in, and we say that this is north and this is south, and of course we have east and west. But when we talk about a bearing, what we're typically doing is we're describing the direction something's going in by telling how far east or west it is from north or south. So for instance, if I said north 60 degrees towards the east, what I mean is start up north and I want you to deviate 60 degrees down this way. So if I'd say that this is 60 degrees right here, we'd say that this is the direction I'm traveling in, but only because I started up north and went 60 degrees towards the east. Whereas if I started this house, south, and say south like maybe 20 degrees west, south 20 degrees west would mean start down south and go 20 degrees towards the west. This is the direction that you're heading in if you're south 20 degrees west. So we want to describe this right here. So the first thing we're going to do is we're going to imagine this imaginary north-south line running through this here. And we say that this is north and that this is south. And of course then this is east and this is west. And maybe I should have put this in green. So we say north, south, east, west. What we're going to attempt to do is to find how far we've gone deviating right from north by using the law of cosines here. So anytime you have an application problem like this, I already know what it is that I want to solve for, and I've already set up the situation. Maybe it's a good idea to redraw the situation. So I notice that I have a situation that looks like this, where we're calling this point A, the vertex A. We'll call this vertex B and this vertex C. And I already know that this is 60 miles. Okay, we know that this is 80 miles. And we also are aware that the third side, 80 miles, the third side is 139 miles. So what we're going to do is this. If we're going to find the bearing here, then we're going to need to know some angles of this triangle, and I'm really interested in finding the measure of angle B. So like any time we have a situation where we're using law of sines, law of cosines, it's very beneficial to label out your vertices using capital letters. A, B, and C are the ones I choose here. So we say capital A, capital B, capital C. I don't know the measure of any of those angles, but I do know that lowercase a, which lives across the street from A, which is this 80 miles, is this one right here. So we say 80 miles. And then we say lowercase b, which lives across the street from this uppercase b here, we say is 139 miles. And then we say lowercase c, which lives across the street from uppercase c, is 60 miles. So those are our side lengths. We can see that if my job here is to go solve for angle, and it seems that we desire angle B here, my first inclination is could we use the Pythagorean theorem? And unfortunately this is not a right triangle, so we can't use Pythagoras. Also, could I use the law of sines, which means I would have to have both a side length and its angle opposite. And I have no side angle pairs here when I look through this matrix of data. So what we're going to need to do is rely upon the law of cosines. Now remember, the law of cosines looks like this. A squared equals b squared plus c squared minus 2bc times the cosine of a. Now, in previous videos, I pointed out that there are three alternate forms of this formula. We could have b squared equals a squared plus c squared, where this is now 2ac cosine of b. But what I want to point out is this. Whatever side length I start with, we say that thing squared is equal to the sum of the squares of the two other side lengths over here. So it looks very Pythagorean. And then I also noticed that if I had a b and a c here, this is always minus 2b times c. I'd put those here, and I end with the angle of the side length that I started with. So that's how I remember the second one down here. We say b squared equals, well, the sum of the squares of the other two sides. Since this is an a and this is a c, then I know this is minus 2ac, and this has to be cosine b only because I started with side length b. So we're going to adopt this second formula right here, and it's a very good thing that we took the time to write all this out, show our work, because what we're going to do is plug in everything we know. We say b squared equals a squared plus c squared minus 2ac cosine of b. We're going to go start dropping numbers in where they need to go. So we say b squared, this is 139. We say a squared plus c squared, so 80 squared plus 60 squared, and this is going to be 80 and 60, and we just don't know b. So this is going to be the thing we're looking for here. So the important thing is that we've got to get this trig function by itself, just like we've solved equations before. So we're going to go ahead and get our calculator out to kind of help us evaluate some of these larger values. We say 139 squared is going to be 19321, so we have 19321. We're going to take our time on this. 80 squared would be 64 with 2 zeros. 60 squared would be 36 with 2 zeros. Now, 2 times 80 times 60. I am going to check myself on this one. Sometimes I make mental math errors. 2 times 80 times 60. We get 9,600. So we say minus 9,600. And this is times the cosine of b. Now, one thing I want to point out here on this is we still got to get cosine b by itself. But most of the time I get people that combine these out, which like they should. 19321 should equal, when you combine these, you get 10,000. And this is minus 9,600 cosine of b. I just want to point this out because this is wrong. But we cannot combine these two things. Cannot combine. And the reason why we can't combine them is because one has a cosine tacked onto it, and the other one doesn't. One's just a constant. So what we're going to do is this, a two-step process. We're going to take away 1,000 from both sides, or 10,000 from both sides, pardon me. And so that's going to isolate this. So over here on this side, we get 9,321, and then this is equal to a negative 9,600 cosine of b. So now we're going to divide both sides by negative 9,600 to isolate this trig function. When I divide a positive by a negative, of course, I get a negative. But here's where I need my calculator. We're going to say that all of this, of course, equals the cosine of b. So the cosine of b is equal to approximately, let's do this, we say 9,321 divided by 9,600, which is negative. We get this thing right here, negative 0.9709-ish. So it's approximately negative 0.9709. If we had ever run across this in any former problems that we've done, we'd say, well, what we do now is just do the cosine inverse of both sides. So we get then b is equal to the cosine inverse of this thing right here, 9,321 over negative 9,600, which is approximately 0.9709. And it's negative. So we're going to get our calculator out now. And actually, I'm going to take the cosine inverse of all of this since I have it all available to me. So we say second, and cosine inverse is right here. And I am in degrees, so 166.15-ish degrees. When you talk about an angle, let's go out one decimal place. So we say about 166.2 degrees. So angle B is 166.2 degrees. Now, first things first, I always recommend going and putting this on the triangle where it's supposed to fit and say, is it reasonable? I think this is totally reasonable. But the next thing I want to confront is this. What we really were finding was a bearing. I wanted to know how far east from north were we going here. And so again, if we were to kind of superimpose an imaginary north-south line here, what I could tell you is at least this. Here's our east-west line, that this makes a right angle down here. And so if that's a right angle right there, but from here all the way over to here is 166.2, what we can do is we could take that 166.2, 166.2, and we'll subtract off 90 of those degrees to get rid of this left side over here, and it leaves behind this part right here, which is 76.2. So to answer our original question, we say that this is a 76.2 degree angle right here, from here over to here. 76.2 degrees. So what we're going to say is the bearing of this ship. All we had to do was find the angles, but we say the bearing of the ship is north 76.2 degrees towards the east is where we were going. Notice that we had to find this angle first. Cheers.